Hello everybody. In this video, we're going to learn about the chain rule for multivariable mathematics. But before we talk about the multivariable mathematics version, let's review the chain rule from Calculus 1. So in Calculus 1, the chain rule helps you find the derivative of a composition of functions. So in particular, if you have a function y defined as f of g of x, the derivative y prime is equal to f prime of g of x times g prime of x. Sometimes this is informally remembered as the derivative of the outside times the derivative of the inside. Whatever works to help you remember it. As a more concrete example, consider the function y equals sine of x cubed. Here, the outside function corresponding to f is the cubing, and the inside function is sine of x. So to calculate the derivative of this function, we first calculate the derivative of the power 3, so that's 3 times the inside function squared, and then multiply it by the derivative of the inside function. And the derivative of sine x is cosine x. So the derivative of this function is 3 times quantity sine x squared times cosine x. Now, you may have also learned this in an alternative notation, which turns out to be much more useful for understanding what we're going to do in multivariable mathematics. So instead of writing a function as y equals f of g of x, we introduce an intermediate variable u. Let this inside function g of x be equal to u. And then y is equal to f of u. In which case, if we want to calculate the derivative dy dx, it's equal to the derivative dy du times the derivative du dx. So, as an example, let's take a look at the previous example recast in this new u notation. In this case, we could say u is equal to sine of x, and y is equal to u cubed, in which case the derivative dy dx is dy du, the derivative of u cubed is 3u squared, times du dx. The derivative of sine x is cosine x. Then to see how this leads to the same answer that we saw before, remember that u was defined as sine x, and you could substitute that in this expression for u. And you'll see that you get the same answer in either way. Now, it would be very helpful to visualize this process as kind of a chain almost. Here we have y, which depends on u, and u, which depends on x. And so as x changes, we kind of accumulate changes at each stage of this chain. Right? The way that u affects, or the way that x affects u is measured by du dx. The way that u affects y is dy du. And then, well, the total rate of change along this chain is dy dx equals dy du times du dx. So we multiply these contributions. Now, really the only difference in multivariable math is multiple variables. So in particular, we must take into account all the ways in which one variable might affect another one. For example, let's say we have z equal to a function of x and y. We've worked with functions like this before, but let's further assume that x is a function of t and also y is a function of t. So if there is any change in the variable t, that's going to affect z, but in two different ways. It affects z through x. It also affects z through y. And so we might create a dependency diagram like this in the lower left corner. Z depends on x and y, x depends on t, and y depends on t. And in particular, there's 4 different derivatives which are of interest. There's the partial derivative dz dx and dz dy, and these are partial derivatives because the formula for z has multiple variables in it. Then there's the more standard derivatives dx dt and dy dt, because both of these functions just contain the single variable t. Now, as we've seen before, when we're dealing with a chain rule for a single variable, we multiply the derivatives along each chain. And so here we can get from z to t through this left-hand side of arrows, and that contribution is dz dx times dx dt. We can also arrive at t through this right-hand set of variables, and so this contribution would be dz dy times dy dt. So we multiply contributions along each path, and then we add the total contributions from each path. Right? So the chain rule to calculate dz dt would be written in this way. It almost looks like you're adding up two chain rules. So as an example, we're going to solve this problem in two different ways. Let's say we have the function z, it's a function of x and y, and it's equal to x times y squared. Let's furthermore say that x is a function of t, equal to t squared plus 3, and y is a function of t, equal to 5t plus 4. Now the chain rule we just discussed says that dz dt is equal to dz dx times dx dt plus dz dy times dy dt. So we need to calculate each of these derivatives and then combine them as specified by this formula. dz dx, the partial derivative of this function with respect to x, is x times a constant, so that constant y squared. dx dt, see the derivative of t squared plus 3 is 2t. dz dy, the partial derivative of a constant times y squared, is going to be 2 times a constant times y, 2xy. And dy dt, at the derivative of 5t plus 4, that's 5. And so that's your answer right there. And depending on what kind of a problem you have, you could theoretically stop there. Right? If you have values for t, x, and y, you could plug them in at this point and then be done. But just to illustrate that there's more than one way to do a chain rule problem, you could also convert all variables into t. The way you would do that, well, we have an expression for x in terms of t and an expression for y in terms of t. So every place we see a y, we could put 5t plus 4. Every place we see an x, we could put t squared plus 3. And then we could distribute all of this out, and when we're done, combining like terms, we end up with a derivative 100t cubed plus 120t squared plus 182t plus 120. Or, here's a second way we could do this problem. Z is a function of x and y. We could immediately start by plugging in the expressions for x in terms of t into the original function, and for y in terms of t into the original function. So we could plug those in, and we have 5t plus 4 quantity squared, so we could expand that out, and then distribute and collect like terms. We end up with this expression here, and then we calculate dz dt in the ordinary way. It's just a bunch of power rule applications, and we find that the derivative we get, it precisely matches the derivative we calculated previously. And so there's more than one way to do this. Now, what does this mean geometrically? So, for this kind of a problem, where z is a function of x and y, and x is equal to g of t and y is equal to h of t, let's define a vector function c of t, where the x component is given by the function of x, or the function for x in terms of t, and the y component is the function for y in terms of t. And so this vector function c of t, we can imagine it in a three-dimensional space, but c of t could trace out a curve in the xy plane. Maybe this is t of 0, t of 1, t of 2, t of 3, t of 4, t of 5. So we have this curve down here. Meanwhile, we have our surface, z is a function of x and y. So I've drawn that here. this mountain shape. This is my favorite three-dimensional diagram to draw. It's one of the few that I can draw acceptably well. And this is going to represent our surface, the multivariable function. What does the composition of the functions represent? What is f of c of t? Right? Well, c of t means we're plugging in the points along this curve into the function f. Right? So for this x and y value, we plug it into the function f and we get a z value. That corresponds to this purple point here. We take this next xy point and we plug it in and we'll get another point on this surface. Each point on this curve in the xy plane corresponds to a point on this curve embedded within the surface. So it's like we're carving out a path contained within the surface when we do a composition of functions. Now, to continue, I'd like to reintroduce something called polar coordinates, which turn out to be surprisingly useful. Polar coordinates give us an alternative way to specify locations on the plane. They're specified with the letters r and theta, and ordinary coordinates x, y, they measure displacement along an x-axis, followed by a perpendicular displacement along the y-axis. So we might refer to this point here with the coordinates x, y. Alternatively, we can specify where this point is by first saying how far away it is from the origin, right, measuring the distance of this dashed line here, and also specifying the angle between that segment, corresponding to r, and the x-axis. Right, so theta is this angle here. It's as if, to locate this point, you were to begin by standing at the origin, facing the positive x direction, and first turning by a certain angle, and then moving forward by a certain amount. You can use that data to locate any point in the plane. Now, the xy coordinates or r theta coordinates, whichever coordinate system you use, there are ways to convert back and forth. The reason being, these values very nicely correspond to parts of a right triangle. In particular, a right triangle with angle theta down here. Right, we can use a few key facts about a right triangle, in particular, the Pythagorean theorem, x squared plus y squared equals r squared, can be rearranged to give you a formula for r in terms of x and y. So if you're given x and y values, you can figure out r. Similarly, skipping ahead a little bit, the tangent of this angle, theta, is equal to the length of the opposite side divided by the length of the adjacent side in a right triangle. So we know that tangent theta is equal to y over x. Now this equation can be rearranged to solve for theta in terms of y and x. Apply the arctangent function, or the inverse tangent, to both sides. That cancels out the tangent on the left, leaving you with just theta. And on the right, you have arctangent of y over x. Right, so again, if you're given x and y, you can use this first formula to determine r, and this last formula to determine theta. Alternatively, if you're given r and theta, you could solve for x and y. And this uses two other trigonometric functions. The sine of angle theta is defined as the length of the opposite side divided by the length of the hypotenuse. So sine theta is equal to y over r. Multiply both sides by r, and you have a formula for y. Y is equal to r times cosine theta. So if you know r and theta, you could determine y. Similarly, cosine of an angle theta is defined as the length of the adjacent side divided by the length of the hypotenuse. So cosine of theta is equal to x over r. Multiply both sides by r, and you have a formula for x in terms of r and theta. X is equal to r times sine theta. So again, given r and theta, you could solve for x. Now, why is this useful in talking about the chain rule? Well, these derivatives with respect to r and theta give you different information about a curve. So let's say, for example, we have some vector function, c of t, representing a parametric curve in the plane. Right, so the x-coordinate is given by the function g of t, and the y-coordinate is given by the function h of t. So over here, here's an example function, gets to point A, and then to point B, to point C, to point D, and so on. These derivatives, dr dt and d theta dt, give you more information about what's happening as you move along this curve. Dr dt is the rate of change of distance from the origin. Right, so here, when you get to point A, right, you're getting a little bit closer to the origin, so dr dt would be negative at this point. Your distance from the origin is decreasing as you get closer. Right, at this point this point C, you're moving away from the origin. So at this point, dr dt would be positive, indicating that your distance from the origin is increasing. d theta dt corresponds to the rate of change of rotation around the origin. So while you're traveling around this curve, maybe you're rotating around the origin, or maybe you're not. So for example, at this point B, right, the curve is going around the origin counterclockwise here. So d theta dt would be positive here. At this point C, you're just moving away from the origin. Right, so your angle that you're making with the x-axis really isn't changing at this point. At this point, d theta dt would be 0. And here at point D, you're kind of moving in a more clockwise direction. That's the opposite of the standard direction. So here, d theta dt would be negative. And so this is describing, these two derivatives are describing different kinds of motion around the origin. Now, how could you calculate these, especially if you just have a function in terms of x and y? Well, you can calculate how r depends on t and how theta depends on t using a chain rule. And over here is the dependency diagram. Right, so r, as we saw, the formula for r involves both x and y. And x and y both depend on t. So any change in t affects x through two different chains, from r to x to t, and from r to y to t. So the chain rule for dr dt is dr dx times dx dt plus dr dy times dy dt. Meanwhile, the chain rule that helps you calculate d theta dt, well, there's two ways in which a change in t would affect theta, again, both through x and also through y. So the chain rule states that the formula for d theta dt is equal to d theta dx times dx dt plus d theta dy times dy dt. So let's try calculating an example. So here are the parametric equations for the trefoil knot curve. A trefoil because it looks like it has 3 crossings. It also looks like a delicious pretzel. So in this equation, we like to determine what's happening right here at this point, t equals -1. And this is t equals -2, then -1, then 0. So we'd like to determine how quickly is the distance between this point and the origin changing. In order to calculate that, we'll use the chain rule. First, we know that x is the function t cubed minus 3t. So when t equals -1, x equals 2. The derivative of this function, dx dt, is 3t squared minus 3. And again, when t is equal to -1, we substitute that value in, and we see that dx dt is equal to 0. And as a geometric interpretation of that, that means at this point, really it's moving straight up it's not really moving to the left or to the right at t equals negative 1. Let's examine the behavior of y. So y is the second component function, t to the fourth minus 4t squared. When t equals negative 1, y equals negative 3. Also, the derivative of the function is 4t cubed minus 8t. When t equals negative 1, this derivative, dy dt, is equal to 4. Right, so in this case, the point is moving upwards. That's what this derivative tells us. But again, we'd like to determine what's dr dt. How's the distance from the origin changing? Well, r is the function square root of x squared plus y squared, which we could also write as the quantity x squared plus y squared to the 1/2 power. Well, to calculate the partial derivative with respect to x, we need a chain rule. While we're calculating our chain rule, we need another chain rule. So this is going to be 1/2 of the inside function to the negative 1/2 power times the derivative of the inside. Since this is with respect to x and y is a constant, the derivative of the inside is 2x. Rearranging these terms, these 2's cancel, the x goes into the numerator. This negative exponent means this is in the denominator and is a square root. So this derivative is x divided by the square root of x squared plus y squared. We have these values of 2 and negative 3. We can put them into this formula. And here is the partial derivative of r with respect to x, 2 over radical 13. We do a similar calculation for the partial derivative of r with respect to y, and we get y over the square root of x squared plus y squared. Again, substituting the values for x and y, we get dr dy is equal to negative 3 over square root of 13. So now we have all the derivatives we need for the chain rule. We have dx dt, dy dt, dr dx, and dr dy. We assemble the pieces together, as given by the chain rule formula, and we calculate that dr dt is equal to negative 12 over radical 13. Right, so radical 13, that's somewhere between 3 and 4, so this is probably around negative 4. So this is telling us, at this moment in time, we're moving closer to the origin. And because it's negative, that distance is decreasing by this number of units in space per unit of time. Now, one more type of chain rule, which we'll commonly encounter, which once again uses partial derivatives and uses polar coordinates. Let's say we have the equation of a surface, z equals f of xy. We can calculate the partial derivatives dz dr and dz d theta. In both these cases, since z measures vertical distance, or the height above the xy plane, these derivatives both measure changes in height. The first one, dz dr, measures your change in height as you're moving on the surface, but away from the origin, or away from the z-axis. And so if we were at this point and we moved away from the z-axis, the height would be going down. dz d theta measures the change in height as you rotate or travel around the origin or around the z-axis. Right, this would be around the origin if you were just in the xy plane, or around the z-axis if you're up on the surface. In this case, it looks as though as we travel around the z-axis, it looks like you're moving up this mountainside. So once again, the chain rules are based on the same idea. We have this diagram which shows how each variable depends on others. Z depends on x and y. Each of x and y depend on each of r and theta. So we have these two chain rules. dz dr is equal to dz dx times dx dr plus dz dy times dy dr. The dz d theta partial derivative can be calculated as dz dx times dx d theta plus dz dy times dy d theta. So as an example, let's say we have the equation z equals x squared times y cubed. Now whenever we're doing work with polar coordinates, it is always the case that x is equal to r cosine theta and y is equal to r sine theta, in which case these partial derivatives with respect to r and theta will always be true. This may be useful information to write down. The partial derivatives of the function z, we've seen this function in a few lessons before. dz dx is 2xy cubed, while dz dy is 3x squared y squared. Once you have all of these pieces, you can write down the different partial derivatives using the chain rule formula. So to calculate dz dr, that would be dz dx, which is 2xy cubed, times dx dr, which is cosine theta, plus dz dy, 3x squared y squared, times dy dr, which is sine theta. Again, you could leave the answer in this form, or if you wished, you could also put everything in terms of r and theta, right, substituting these expressions for x and y in terms of r and theta. When you expand this all out, it actually simplifies very nicely, right? So combining all powers or all terms of cosine theta, all terms of sine theta, all powers of r. Here we have the coefficient 2. This next group has coefficient 3. In fact, you can even add these together to get 5 times r to the 4th times cosine squared theta times sine cubed of theta. Alternatively, you could have the function z and immediately substitute in r times cosine theta and r times sine theta. And if you were to plug both of those in, you would get r to the 5th times cosine squared theta times sine cubed theta. Actually, in this case, plugging something into the original function is slightly easier, because the derivative of this with respect to r, remember everything involving a theta, you could treat that as a constant. So you have r to the 5th times a constant. The derivative is 5r to the 4th times that constant. And sure enough, it checks with our earlier answer for dz dr. You learn math by doing math, so here's an exercise for you to try out. So for the previous example, the one on this slide right here, this function z equals x squared y cubed, write down the chain rule formula for dz d theta, and then find the formula. Right? Plug in the partial derivatives as needed. And if you wish, you can just leave it in this form. That is fine. However, if you have lots of time and want to do some extra math, you could write this all in terms of r and theta. The advantage would be you could also rewrite the original function and check your work to find dz d theta. But you don't have to. You can leave it in terms of x, y, r, and theta if you wish. So this is an exercise for you to try. I wish you the best of luck. And that's how you work with the chain rule in multivariable mathematics. Thanks for watching.